Great. So with that, I'll introduce our last speaker, Dr. Ellen Greene. Dr. Ellen Greene is an assistant professor of operations, information, and decisions at the Wharton School at the University of Pennsylvania. He received his bachelor's degree from Brown University and his doctorate from Stanford University. His research focuses on judgment and decision-making among experts such as professional athletes and referees in sports.
All right, jumping ahead. Thanks, Alice. It's a pleasure to be here. Thanks for having me. Thanks to the organizers. Thanks for the opportunity to share a bit about my work. So it's spring, it's baseball season, so let's talk about home plate umpires in Major League Baseball. So for those of you who are unfamiliar with baseball, here's how it works. Pitcher makes a pitch. If the batter chooses not to swing, then the umpire in black, this guy makes a call, either a ball or a strike. So the pitch intersects this box that denotes the boundary of the official strike zone. He's supposed to call a strike, otherwise he's supposed to call a ball. Only the location of the pitch should determine his call. So what's nice about this context is we have incredibly rich data. So behind home plate of every major league ballpark are stereoscopic cameras that take a sequence of images of every pitch from its release from the pitcher's hand until it crosses the region above home plate on which the official strike zone is implicitly rendered. We have millions of these observations over close to a dozen years now, and we can use them to basically evaluate how good of the job the umpire does. So it turns out umpires do something kind of weird. So here is the plane that rises from the front of home plate. If you were an umpire, you'd be looking through this plane over the catcher's head towards the pitcher. A right-handed batter would be standing to your left where it says inches from vertical midline. The dotted box denotes the boundaries of the official strike zone, so the width of home plate on the horizontal axis and the normalized distance between the bottom of the batter's kneecaps and the midline of his chest on the vertical axis. And then what I'm showing you here with these three elliptical sort of boundaries is the best boundary that separates regions where umpires call strikes on average, that is inside the boundary, from regions where they call balls on average, that is outside the boundary, separately for 3 counts. Okay, so what is a count? It's a state variable that keeps track of the sequence of pitches between a pitcher and a batter over the course of an at-bat. When the count reaches 4 balls, the at-bat ends because the batter walks. When it reaches 3 strikes, the at-bat ends because the batter strikes out. So let me draw your attention first to the middle one, the solid line. So that boundary is in a 0-0 count, the baseline count, the first pitch of an at-bat. So you'll notice this doesn't really look like the box. It's a little bit wider, it's rounded. This is less interesting to us than what I'm going to tell you next. If you basically look at the other 2 ellipses, you'll notice that they're different. So the umpire is only supposed to make his call based on the location of the pitch, but same pitch at the same location, different counts, the umpire is making different calls. In particular, when there are 3 balls and 0 strikes, the strike zone that the umpire enforces is really big. So pitches that he called balls before, he's now calling strikes. The opposite is true when, say, 0 balls and 2 strikes. Pitches that he used to call strikes at, he is now calling balls. So this is odd. When I first saw this 4.5 years ago, I thought, well, it must be the case that umpires are biased, that they're revealing here an aversion to, say, making the more pivotal call, say, in 3 balls and 0 strikes, the call that would end the at-bat by walking the batter, or in 0-2, the call that would end the at-bat by striking him out. In fact, I wrote a paper and got this job based on that paper, but that paper was wrong, I was wrong, and I'm here to tell you what's correct. All right, so imagine that you're the umpire, you're crouched behind the catcher, the pitcher winds up, he throws a 95-mile-an-hour fastball, it's coming to you, and right when it crosses this region where this invisible box is, you blink. You miss the pitch entirely, you have no idea where it was. What are you going to do? Going to make a call. It's on you, batter didn't swing, ball or strike. Maybe you do something stupid, you flip a coin in your head, if it comes up heads, you call ball, if it comes up tails, you call strike, but you can do better than that. You can do better than that. That is, you can make the more accurate call, the more correct call, the correct call with higher degree of accuracy if you rely on your expectations. That is, if you expect the pitch to be thrown inside the strike zone when the batter chooses not to swing, that is when you have to make a call, well, then you should call a strike. And if you expect the pitch to be thrown outside the strike zone when the batter chooses not to swing, then you should call a ball. If your expectations are correct, and by following your expectations, you're going to make the more correct call. You're going to be more likely to make the correct call. Now, this logic applies even if you observe the location of the pitch to the extent that your vision is imperfect. If that's the case, what you should do is you should integrate your noisy observation of where this pitch crossed with your expectations about where the pitch was likely to have been thrown. That is, you should be Bayesian. Okay, so what does it mean to be Bayesian? It means that when you're uncertain about something, you resolve your uncertainty by relying on your expectations of what should happen. Now, we're all Bayesian. If you're thinking about walking into an intersection and a car is approaching but there's a red light, you probably don't hesitate and you take a step because you know that that car is going to stop. You expect that car to stop because in your prior experience, cars stop at red lights. What if you have a coughing fit? Do you have lung cancer? Well, probably not, because you know that many people have coughing fits and very few of them have lung cancer, unless perhaps you're a smoker. What about if you get a positive result on a pregnancy test? Are you pregnant? Well, if you're trying to get pregnant, probably a reasonable chance that you are. If, on the other hand, you're a man, probably not. Right? Depends on your expectations. So how does this relate to umpires? So here's the logic. So imagine that the count favors the batter, so a count like 3 balls and 0 strikes. Well, what does the pitcher do? The pitcher needs to throw a strike, otherwise he's going to walk the batter, so he's going to throw it inside the strike zone. The batter, meanwhile, can afford not to swing. So he may lay off a pitch even if it's in the strike zone. So what should the umpire expect? He should expect the pitch to be thrown in the strike zone even when he has to make a call. That is, even when the batter chooses not to swing. So if it's close, if he's unsure whether it's a ball or a strike, what should he do? He should make the call that he expects, which is a strike. Oops, I pushed this too far. All right, so that was this logic. The reverse logic applies when the count favors the pitcher, say 0 balls, 2 strikes. Here the pitcher can afford to throw a ball, a pitch outside the strike zone, but the batter cannot afford to not swing at anything close, to take a 3rd strike and strike out. So what should the umpire reasonably expect? He should expect the pitch to be thrown outside the strike zone when the batter chooses not to swing. So if the pitch is close, he should call what he expects, which is a ball. So one way to think about what's happening here is that the directive that the umpire faces and his incentives are in conflict. So he's directed, as I told you, to make his calls based solely on the location of the pitch, but his incentives are to make accurate calls. You may initially think that these two things aren't in conflict, but if you as the umpire make different calls and different counts based on the logic that I just described, if you rely on your expectations of where the pitch is going to be thrown that differ in different counts, well, what you're going to do is you're going to make more accurate calls on average at the expense of being inconsistent. That is, you're going to make different calls for pitches at the same location in different counts. Okay, so let me just show you this with an example. So this is that plane that I showed you before. Now we're zoomed in on the top right-hand corner. That X marks the pitch that you see. So you see a pitch just inside the top right-hand corner of the strike zone. Okay, we're going to imagine that you have a flat prior. So what is a flat prior? A flat prior means you wrongly expect every location to be equally likely. Okay, so if you have that prior and you observe a pitch at that location and you follow Bayes' rule as a good Bayesian, you form posterior beliefs that conform to these concentric circles, like a volcano emerging from this plane, a distribution in your mind of the true location of the pitch, which the modal location is right where you observe the pitch. Okay, so what you do as a Bayesian is you just apply a Bayesian decision rule. You, in your mind, you say, is this pitch on average a ball or a strike? That is, you integrate your posterior beliefs over the strike zone. You say, what is the probability that this pitch is a strike? That is, what is the density of my posterior beliefs inside the strike zone? If that's greater than 50%, then on balance, I believe it's a strike, and I'm going to call it a strike. This decision boundary, this black line, represents the point of indifference, basically locations that the umpire observes where half of his posterior are in the strike zone. And so we see that this pitch that he observes to be actually inside the strike zone is right on the decision boundary, and he's more or less indifferent between calling a ball and calling a strike. So this gives us some intuition as to why the strike zone the umpire is enforced is rounded instead of rectangular, because for pitches in the corner, he has to be doubly confident that it's inside both from the top and from the side. Okay, so let's think about a more intelligent set of expectations that an umpire can have. A set of rational expectations, I'll call them, in a count, say, with 3 balls and 0 strikes. Okay, so on the left, I'm showing you just the distribution of pitches, regardless of whether the batter swings. So it's a contour plot. Again, it's a volcano sort of shooting out of the image. And we see that pitchers basically throw right down the center in 3-0. And much of the mass is inside the strike zone. Okay, but in order for the umpires to form their rational expectations, well, they only make calls when the batter chooses not to swing. So we have to think about the batter's behavior. I'm showing you that on the right, the probability that the batter chooses not to swing for every location on the plane. And basically we see here that probability is close to 100% regardless of the location. The batter is almost never swinging. You put those two together. On the left, you get the distribution of pitch locations that the umpire observes when the batter chooses not to swing. It looks similar to what we saw before, the unconditional distribution. And now how does that affect the umpire's beliefs? Okay, so we can do a little calculus. I won't do it explicitly, but what is the intuition behind Bayes' rule? It's that your posterior beliefs move along the gradient of the prior. So let's take a look at that observed location. It's the top right-hand corner. We'll see it right over here. What is the gradient at that point? Well, it's pointing sharply inwards towards the center of the official strike zone. And so we see here on the right, the posterior beliefs move along that gradient in a southwesterly manner. Now when the umpire says, oh, given these beliefs, is this pitch a ball or a strike? He's convinced that the pitch is a strike, even though before he was indifferent with different prior beliefs. His decision boundary moves outward as the posterior moves in. This pitch is clearly inside that decision boundary. He calls a strike. Okay, what about an 0-2? So here on the left, I'm showing you just the unconditional distribution of pitches. This is just saying that pitchers are throwing more or less anywhere now. It's a much flatter distribution. And on the right, what are batters doing? Well, they're being much more discriminating. Pitches inside the strike zone, they're swinging at most of the time. Pitches on the outside, they're trying to lay off of. What happens when you put those two together? We're basically going to eat away all the mass in the center. We're going to get this image on the left. All the mass is now in this horseshoe shape around the strike zone. There's very little mass inside the strike zone. If the umpire believes that he sees a pitch inside the strike zone in 0-2 when the batter chooses not to swing, he should doubt himself because he rarely sees that pitch. Okay, so to apply our logic, we go back to this point right here. What is the gradient? It's pointing steeply outwards in a northeasterly manner. Posterior beliefs move along the gradient. Decision boundary moves inwards. This pitch at the same location, different expectations, different count. The umpire is now sure that it's a ball. Okay, so that was just an example, but let me ask this model, this simple Bayesian model, how well does it do in predicting what umpires actually do? And so what we're going to try to do is just go back to these enforced strike zones, so one for each of the 12 counts. I'm just showing you 3 here. And use our model in a way that I'll defer the details to the paper for, to predict something analogous that we can compare to what umpires do in the data with our prediction of what umpires do if they were Bayesian. Okay. So I'm going to show you 12 slides that look just like this, but the information will be slightly different, one for each count. We'll start in the 0-0 count, the baseline count. On the left, I'm going to show you the rational expectations. That is just the empirical distribution of pitch locations when the batter chooses not to swing in that count. So 0-0, we see a lot of mass inside the strike zone. Pitchers are throwing strikes. And on the right, I'm showing you 2 strike zones. So the solid line is the enforced strike zone that I showed you before. And the dotted boundary is the strike zone that we're predicting from our model. It's assuming a Bayesian agent. Okay, so just one note. So the dotted boxes are different between the 2 images. On the left, that's the official strike zone. On the right, as you may have inferred from this image, basically the strike zone that umpires enforce is considerably wider than the official strike zone. And so we really can't rationalize the data with our model unless we allow the umpires to integrate their posterior beliefs over a different box. And so this is effectively the strike zone that umpires are enforcing according to our model. It's fixed across the count. So they're enforcing something that's a little bit wider than the official strike zone. Okay, but what you'll notice as I go from one count to the next is that as the prior beliefs change, so here as we add a strike, mass moves to the outside. The enforced strike zone is going to change. Here it contracts, and the predicted strike zone is going to contract with it. So there's going to be a lot of change with the enforced strike zone, and the predicted strike zone from our model is going to capture that change. So 0-2, mass moves further out to the periphery. We saw that diagram on the left before. We see the smallest enforced strike zone. The predicted strike zone matches it. 1-0, again, a lot of mass in the center. Big enforced and predicted strike zone. 1-1, migrate to the periphery, contraction. 1-2, more mass migrates to the periphery, more contraction. Again, with 2 balls, this is 2-0. 2-1, 2-2. And then finally with 3-0, 3 balls, we see the largest enforced and predicted strike zones. Contraction with 1 strike as mass migrates out to the periphery. And then finally, in a full count, a lot of mass in the periphery, basically the lower portions on the sides, and we see a smaller enforced and predicted strike zone. So what does this all mean? It means that the decisions that umpires make reflect two things. They reflect really quite a nuanced understanding of what they should rationally expect in each count, and an ability, not explicitly of course, but at least somehow implicitly, to combine what they see with these expectations in a manner that approximates Bayes' rule. And they're doing this all in less than a second, hence the title, Bayesian Instinct. Great, so thank you so much. I'd be happy to take some questions.
You said that the priors are determined in part by experience. We do expect experienced umpires and to have different priors and different results than inexperienced umpires?
Yeah, so one thing I neglected to mention is that every umpire in our sample does this. So we have about 70 umpires, and they all do this to a similar degree. I would expect that, but the umpires that we observe are all the way at the very extreme tail of experience. So, they've done like a dozen years in the minor leagues. They've had some formal umpiring education before that, and we rarely catch an umpire in our data with a little major league experience given low turnover. But even when they get to the major leagues, they're already quite experienced. So yes, I would predict that. We don't have the ability to test it in our data, but I believe the minor leagues are starting to implement these cameras, and so if those data are made public, potentially they can be tested in the future.
Have you been able to inform the umpires of your results, and is it possible for them to change their behavior, or is it just that instinctual at this point that they can't be changed?
Yeah, I mean, I had what I guess would now be a very regrettable interaction with umpires. Earlier, when I went public with the accusation of bias, they predictably didn't like that. Now I feel bad about that, but I haven't gone back to apologize. Maybe I should. It's not clear that they should change their behavior, so it depends what you're trying to optimize. If you're trying to, so let me just be very specific about this. If your vision is imperfect, you are going to do much better relying on your expectations, at least if you apply Bayes' rule more or less appropriately, than if you just rely on what you see. And you can test that for yourself by assuming a blind umpire. He's going to do much better if he just calls based on the count than if he calls based on what he sees. So it depends what you're looking for. If you want umpires to be accurate, then they should be doing this. If you want them to be consistent, then they shouldn't be. It depends on their objective function.
Can it be partially both, that they're using an expectation argument, but then also trying to favor batters in difficult counts and favor pitchers when they fall behind? How would you tease those two apart? And then the second question is, some of those strike zones seem like they were skewed left to compensate for right-handed batters. Mm-hmm. How would that mesh with an expectation argument? Because it shouldn't get skewed left if they're only relying on expectations of the count.
Yeah, so sorry, my memory's bad. So I'm going to answer the second question, and I'm going to ask you to remind me of the first. Okay, so there are a number of reasons that the strike zone is wider and asymmetric than the official strike zone, the enforced strike zone is, and the reasons for them I think are generally uninteresting unless you're a baseball fanatic. It has to do basically with the width, I believe it has to do with the width of the ball, and also with how the umpire is set up behind the plate. And so they set up differently for right and left-handed batters, and that basically, if you look at just right-handed batters, the enforced strike zone is more or less symmetric, but if you look at left-handed batters, there's a huge skew. And I don't think that has anything to do with any interesting behavioral theory. That's just about the prosaics of being an umpire. The first question, remind me.
So the first question was, can it be somewhat of both?
Oh, yes, certainly. I don't think it is, though I can't rule that out. So if it's the first explanation that they're biased in some way, you'd expect first that the bias would be greatest in, say, a count with 3 balls or 2 strikes, and it is, but you'd also expect there to be much less bias in, say, 1-1 or 2-0 than in those counts. And you do see less bias in those counts, but not much less. And in fact, the deviations, say from the baseline count in those other counts, in which the umpire doesn't have an opportunity to really affect the game in any significant way are very well predicted by this model. So I don't see any reason to basically layer on some kind of preference explanation. You'd also expect that things like men on base and number of runs would impact the umpire's calls. Say if it's 0-2 and there are 2 outs, calling a third strike doesn't just end the at-bat, it ends the inning. But we don't see any difference in the rate at which they call third strikes, holding pitch location constant with 2 outs versus fewer than 2 outs. Okay, well, thank you so much.
All right, that concludes our talks for the night. There's food and beverages outside. Thank you for everyone for coming, and a big thanks to the committee that organized and put this all together. All right.